Okay, thank you so much. Thank you so much for the invitation to this great workshop. Unfortunately, my wife is 7 months pregnant, so I cannot come here in person, which is the only reason. Otherwise, I would definitely be happy to come here in person to talk to you in London. And so today I'm going to talk about my joint work with Mali, Mert, Anant, Umert, and some of you already met some of them at the workshop. Um, Okay, so let's see. Everybody knows that a lot of machine learning problems eventually boils down to a population risk minimization problem, such as equation one. So the goal is to minimize the expected value of a certain loss function. And so here X is the parameter of all the neural network, and the Z is a random a data point distributed according to some unknown a data distribution D. And so for machine learning task, whenever you have a deep learning, typically F is non-convex in X. Now, of course, since distribution D is unknown, what people usually do is to consider the empirical risk minimization instead, which is given by equation two. So given that you have access to an IID, a training data set Z1, Z2, Zn, and then you look at the empirical risk minimization according to equation two instead. Now, um, everyone uses a stochastic gradient descent and its variance. And so stochastic gradient descent is one of the most popular algorithm for solving empirical risk minimization. So it's given by equation three. So here, instead of computing the full gradient, you compute a stochastic gradient. So one of the common choice for stochastic gradient coming from the mini batch. So here, instead of sampling over all the n data points, you just randomly, uniformly choose B of them. So B is the batch size. And so this provides unbiased, conditionally unbiased estimate for the full gradient. So this is a stochastic gradient descent algorithm. Now it's widely used in machine learning tasks, and the people also find it has very good generalization properties. So generalization just means that it works well for unseen data. Now, why is it working well for unseen data? There are many different speculations or explanations. So one of them is the so-called wide minima phenomena that dates back to more than 2 decades ago. So basically, they argue that the SGD, they prefer those wide or flat minimum. And so the paper from 2017, a few years ago, they argue that depending on the ratio of eta over b, so eta is the step size, b is the batch size, it determines the flatness of the minima found by SGD, and hence the difference in generalization. So essentially, SGD, they find those flat, wider minima, and that's the reason it caused a better generalization. And yesterday, in Mert's talk, he talked about our joint work about how to rigorously quantify the tail index given the choice of eta and the b, and how to quantify the tail index for the SGD. So now, on the other hand, people also observed empirically that gradient descent is basically just without a stochastic gradient, it's just deterministic gradient, does not work well in terms of generalization. And so the only difference between the gradient descent and the SGD is the stochastic gradient noise. And so there are many approaches to understand this better. So one popular approach is just to approximate the gradient noise by let's say a Gaussian random vector psi k. And then you can just approximate the SGD by equation four. So replacing the gradient noise from the mini batch by some Gaussian noise. And so if eta, the step size is small, approximately speaking, equation four can be viewed as so-called overdamped Langevin SDE, driven by a Brownian motion. Now, it's possible that people have already talked about this metastability phenomena in this workshop, but let me just briefly mention this again. So there's something in applied probability called Arrin-Cramer law, which originates from the Arrin and the Cramer physics people, but dating back to 1930s. But of course, they didn't prove them rigorously. And so the idea is that let's say if you look at a double well, which can be generalized to multi-well situation. Let's say you have a double well, And you want to ask like, okay, you have two local minimum, M1, M2. So on average, how long it would take to go from M1 to M2? Well, like the leading order term, it turns out to be exponential, and that exponent can be like computed out using some like a large deviation theory, like a Friendly-Wenzel like type of large deviation theory. So when people talk about Allen-Cramer law, it mainly like refers to they can also work out the prefactor term, which like is done by using potential theory. But anyway, so here you can see like the in terms of the leading order term, it's e to the power f0 minus fm1 divided by epsilon. So here like f0 minus fm1 is associated to the height of the well. So basically, if the Brownian motion-based overdamped Langevin serves as approximation of the SGD, that suggests that the SGD will stay longer in deeper like minima instead of those like wider flatter minima. And that contradicts the wider minima phenomenon. And so that's the argument used in in this paper to argue that like a Brownian motion noise is not a good approximation to the gradient noise. Now, if the Brownian motion noise is not a good approximation, then the second natural thing to go for is the alpha stable distribution, which appears in the limit of the generalized central limit theorem. And so alpha stable distribution is a heavy tail distribution. So this way, you can approximate SGD by equation 6. So instead of the Brownian noise, you just like use the alpha symmetric alpha stable noise to approximate the SGD. Now, if eta is sufficiently small, the step size is sufficiently small, then essentially you are looking at a continuous time Levy-driven SDE. So equation 7 is essentially a continuous time Levy-driven SDE. So for that, there's a metastability result coming from statistical physics literature, which says that like if you look at like a bunch of like local minima Mi, they are separated by like several local maxima Si. And so in that 2007 paper, they proved that like after certain scaling, this Levy-driven SDE will converge to a continuous time Markov chain. And that continuous time Markov chain will just concentrate on those like local minima. So, I mean, the idea is very simple. So essentially, like, let's say originally you have some like Levy-driven SDE like on this landscape. But you can imagine that like once you are the only way you go from M1 to M2, because Levy process is a jump process, is for you to jump like outside. Right? And so if you don't have a big enough jump, and then it's just dynamical system, it's just ODE, and it will like very fast like go back to M1. And the same principle applies to the another like a local minimum here. So the idea is that most of the time, actually, it will just concentrate around M1, M2, except that occasionally you have some big jump and then you just go to the next well. And now for that, you can explicitly compute the limit, which is a continuous time Markov chain supported on this finite state space consisting of the local minimum. And then for the double well example, you can even compute that there exists a unique station distribution, pi1, pi2, and with explicit formula for pi1, pi2. And then you can see that pi1 is bigger than pi2, that validating the wide minima phenomena, because like that means like on average in the stationality, it will spend more time around the local minimum M2 instead of M1. And so it basically is consistent with the wide minima phenomena, wide minima phenomena. So so this is like a relatively brief introduction. So I went them relatively quickly because I think some of most of you are already familiar with this type of argument. And so we have seen that like heavy tails can help like SGD find the wide minima. And now it's also believed in the computer science literature that wide minima is the reason why SGD have better generalization performance. So, but unfortunately, this is just some heuristic argument, right? So it doesn't prove rigorously how heavy tails can help SGD with generalization performance. So how to do that rigorously? So that's the focus of today's talk. So in machine learning, there are usually two approaches to prove generalization performance. So one approach is algorithmic stability. So that's the focus of today's talk. Another approach is information theoretical based approach. And so that's also like a popular approach. So for algorithmic stability, essentially what it is that like if let's say you have empirical risk minimization, okay, problem, which is given by equation 9, and then of course like the output of the empirical risk minimization problem is the SGD. So let's say at a case iterate you stop and you get the output, and that output depends on the data set. It depends on the training data set. Zn. So Zn consists of Z1, Z2 to the Zn. So that's the training data set. And of course, you want to understand. So algorithmic stability is about if you give me a two very different data set, very similar data set, like let's say if they are just different by at most one element. And then you can imagine that the resulting output should be very close to each other. And then the question is that how do you quantify how close they are each other if you start with slightly two different training data set? So that's the subject of like algorithmic stability. And so if you have algorithmic stability, then basically like there's some existing theory which says that like algorithmic stability bound can lead to the generalization error bound, which is not surprising. I mean, that's very intuitive because like generalization is about like whether it works for unseen data, right? So if you already work well for the training data, if you give me a new data point, does it work well, right? So you can imagine that like it's very closely associated with algorithmic stability. So this is just like some more formal definition of algorithmic stability. So I quoted the Hart paper from 2016. So essentially, like if you have a loss function, let's say surrogate loss function here, so A is the algorithm output. A is the algorithm output. Z is the data set. Z is the training data set. And the Z hat is a slightly different data set. So basically Z and the Z hat, they differ by only one element. And then you want to like look at, okay, so in the expected in the expectation, whether they are close to each other or not, like, and then like it's epsilon uniformly stable if in the expected value takes the premium over like a data set and they are close to each other. So that's called like epsilon uniformly stable. So basically the goal is to show like how to investigate the algorithmic stability for heavy-tailed like SGD. Now, as I mentioned, like in the machine learning literature, people understand that like algorithmic stability is closely related to generalization performance. So here, the expected generalization error bound given by this like left-hand side of equation 12 here is bounded by epsilon. Suppose the algorithm is epsilon uniformly stable. So in essence, it means that like if you can show that the algorithm is epsilon uniformly stable, then like the expected generalization error bound is also upper bounded by the same epsilon. And so here like R hat is like the empirical like risk here. So R is the population one. It's the population one. And so when you look at the difference and the take expectation, etc., etc., so that's the expected generalization error bound. Now let's go back to our problem. So we already like we want to understand how the heavy tail can help SGD generalize. So because of that, we look at a heavy tailed like a continuous time heavy tailed approximation of SGD. So in our paper, we also consider like a discrete time case. So it doesn't have to be like continuous time, but in this talk, to be more simple, like I just illustrate through the continuous time version. So equation 13 is the continuous time approximation of the heavy-tailed SGD that like we previously already mentioned. So here LT alpha is a alpha stable like a Levy process. But if you are a mathematician, you want to get technical. So I want to mention that like in our paper, we just assume it's like rotationally invariant. Because like for Brownian motion to go from one dimension to high dimension, it's basically there's no ambiguity. But for alpha stable Levy process, when you consider high dimensional alpha stable Levy process, you need to specify like whether it's rotationally invariant or it's like some other type of like a Levy process, like a cylindrical, like IAD components type. So we look at a slightly different data set, Z hat. So Z hat n is slightly different from Zn by at most one element. So because of that, it results in a slightly different like Levy-driven SDE, which is given by equation 14. So here, like it's basically just depending on Zn hat, Zn hat. So the output is essentially like the xt from equation 13 and the xt hat from equation 14. So here, like we are interested to look at like a uniform bound in T. So we can even take T to be plus infinity. We can take T to be plus infinity. And so like if you look at like some Lipschitz like a surrogate loss function, let me call it like a little L here, then there's a nice paper by Maxim Raginsky, which showed that like okay, so if you look at like Lipschitz like surrogate loss, and you want to quantify the generalization error bound, then basically you can upbound it by the Wasserstein like a Wasserstein distance. So W1 here is the one Wasserstein distance between the law of like xt and the law of xt hat. And so here like it's taken over the supremum over all the possible like Zn close to like Zn hat. Zn close to Zn hat. So now at this stage, we already boiled down this like to a mathematical problem. Essentially, like you have two Levy-driven like SDE, and so the drift term, they have some difference, and then how to quantify the Wasserstein one distance between these. And this we can directly lead to the generalization error bound. Now, when we first approached this problem, let me think, it was like a 2022. And so Umert, myself, like and Mali, we had no clue, and so we don't know how to do this. Like also like Anant, like we don't know how to do this, and so we thought that we should start with the simplest case. So the simplest case is the loss function when f is quadratic. When f is quadratic. Now, if f is quadratic, it essentially reduces to some Levy-driven like Ullsten-Uhlenbeck process. So it's, I mean, this least square problem will like be equivalent to some like a Levy-driven OU process. Now, which reduces to equation 16 and 17. So for Levy-driven OU process, it's easy to work with because one can explicitly compute out the characteristic functions of xt and xt hat. Now, the characteristic functions uniquely determines everything about the distribution of xt and xt hat. Then what you do is that like you apply some inverse Fourier transform, and you do some careful analysis, and you are able to obtain the generalization performance, I mean, the algorithmic stability and generalization performance for the Levy-driven OU process. And then actually one can rigorously show that there's a parameter alpha 0, which is kind of like a threshold. So alpha 0 is less than 2. And then one can show that the generalization error like increases in alpha when alpha is between alpha 0 and 2. So that means like in that region, at least, that actually the heavy tail helps to make the generalization error smaller, So that's like the paper we published last year at like algorithmic learning theory like conference. But this is only like for the quadratic case. So our numerical experiment supported the theory beyond the quadratic case. So the numerical experiment, we are able to look at like a neural network. So let's say like we look at the 3 different data sets, like image data set, like means the CIFAR 10, CIFAR 100. So the y-axis is about the test accuracy. Is about the test accuracy. So higher test accuracy, the better the generalization. And the x-axis here is about the tail index. So we basically estimate like tail index alpha hat for each model, like using different like training ratio for like eta over b. Because as you seen in Mert's talk yesterday, like a different choice of eta over b can lead to like a different like heavy tailness. So essentially, if you choose larger value of eta over b, you need to have heavier tail. So alpha hat is the x-axis. So basically, this is the estimated tail index. So 1.77, like so the smaller alpha hat is, the heavier the tail. So so here, like you can see that like when we look, you do the estimate like the tail is not that heavy, it's usually between like 1.77 and 2.0. But of course, 2.0 is basically means no heavy tail. And so here we look at like several like examples like for the fully connected neural network with a 4-layer, 6-layer, and also look at convolutional neural network. The overall trend is like roughly speaking like a U shape. It's like an inverse U shape. The overall trend is an inverse U shape. Inverse U shape just means like the test accuracy gets better when you decrease the tail index a bit. So when the tail gets heavier. But if the tail gets even heavier, uh, and then basically it doesn't help with the test accuracy. It doesn't help with the test accuracy. So you have this like a monotonic, like an inverse like U shape. But that's actually consistent with the theoretical result from the quadratic case because like we mentioned that there exists an alpha 0, right, between 0 and 2. And so in that region, you have generalization error like increases. And it's not like always monotonic like for any alpha. But then the next question, like which is the main focus of the talk today, is about like how to come up with a theory to deal with the general loss function. So because like we've seen that the numerical result overwhelmingly suggests those like inverse U shape, which suggests that the heavy help generalization error bound. And there's also some like a non-trivial non-monotonicity. Like it's not a monotone. It's like basically inverse U shape. And then like for the quadratic case, because it corresponds to the Uster-Uhlenbeck process, we know how to analyze it. But then the question is how to deal with the non-quadratic case. Now, for the non-quadratic case, I want to mention that there are several difficulties. One difficulty is that like we want to deal with non-convex loss function. We don't want to look at like convexity. We want to look at like a non-convex loss function because I think a heavy-tailed like SGD, like this heavy-tailed phenomena is most interesting when you look at the non-convex landscape. And this is like a challenge number one. So you have non-convexity. And the challenge number two is that like you can imagine that like by using some ground wall inequality or some elementary tool from probability like type of stuff, you can obtain some algorithmic stability type of stuff on a bounded time interval. You can imagine that like because like as time evolves, right? If Zn and Zn hat are close to each other, like you can always obtain some algorithmic stability. But the challenge is that like we are interested to obtain some uniform in time like algorithmic stability that allows time t goes to infinity. Because we are not interested, let's say, to get algorithmic stability that will grow exponentially as time grows. And that's not what we want. And that adds like a second difficulty. And then the third difficulty in terms of technical challenge is that like in the literature, when you look at like algorithmic stability, usually they deal with like a stochastic gradient Langevin dynamics, where they have like a Gaussian tail here. They have like a Gaussian tail here. So if you have Gaussian noise, or if you just have gradient noise with a bounded second moment, and then it's much easier to work with like the to control the expected value to work with the Lyapunov function because like you can just do the square function as the Lyapunov function. Here, it's heavy tail. If it's heavy tail, then basically there's no guarantee the second moment is finite. Actually, it's infinity. And so the question is that then how do you design a Lyapunov function that makes it work? And so this type of thing like brings like three technical challenges. Now we still need to make some assumptions. And so we will try to make the assumption as weak as possible. So we obtained this like very algorithmic stability result for this general loss function, heavy-tailed general loss function SGD in our last year's ICML paper together with Anand, Mert, and Umert. So first we impose a pseudo-Lipschitz type condition. So that's actually commonly used, like for example, it's used in Adokdu's paper, Murat's paper. So basically we assume that there exist universal constants, K1, K2, such that like it's not just only Lipschitz, like in the parameter x. So if x is close to x hat, and they are close, but also like z. So the data point, if z is close to z hat, and then basically like you also have closeness. But of course, like to make sure that it's satisfied by a lot of like examples, people of interest, we need to like allow some like dependence, a linear dependence here on x and x hat, because otherwise a lot of models will fail like this assumption. And another assumption we make is commonly used like in the non-convex, like SGD or Lingjiong literature with the dissipivity condition. So that's basically weaker. That's weaker than the like a strong convexity condition. And actually, it's slightly weaker than strong convexity outside of a compact domain that people used in several papers, for example, like in Michael Jordan's paper. And so essentially, we assume the dissipivity condition. The dissipivity condition guarantees that, like, okay, so you don't have strong convexity, but at a global level, like at the global level, you kind of have certain kind of like a quadratic like a type growth. And so that's what the dissipivity condition is about. And so basically it's like a commonly used assumption in the non-convex like literature. And now, of course, we also mentioned that like in our paper, in order to study discrete time heavy-tailed SGD, one can even impose a stronger assumption. So here, this assumption is enough if we just look at it like a continuous time case. So if you want to look at a discrete time case, yeah, then you need to even impose a slightly stronger assumption on the loss function. So under these assumptions, in our last year's ICML paper, we are able to obtain first like the Wasserstein like a stability bound. So here like let's say let mu and mu hat to be the invariant distribution of xt and xt hat. As t goes to infinity. Now, of course, like I didn't like show this, but like under our assumptions, it's known in the literature that is like these dynamics have a unique invariant distribution. Okay, and so but of course our bound we also have bound in our paper that's for like any given t here, just to make the illustration simple, we just look at the case when t goes to infinity, comparing the invariant distribution as t goes to infinity when you have like two slightly different data sets. And then basically we obtain this like Wasserstein stability bound. And so those like C1, lambda, etc., they are all some positive constants that can be spelled out explicitly. And also like C0, C1, K2 here. Now, one important term here is the like a low Zn hat. That's essentially kind of like some distance between the two data sets, Zn and Zn hat, Z and Z hat. And here is basically the average of the distance between Zi and the Zi hat. Remember that like Zi and the Zi hat are just the ith data point from two slightly different data sets. And then actually, because remember that like we assume that like these two data sets are differ by only one element. So actually, except at one point, every other point like this quantity is actually zero. So this low Zn hat is of order like 1 over n. If is of order 1 over n. So if we like apply like to some surrogate like L. Lipschitz like loss function, and then assume that the data set is bounded, let's say it's uniformly bounded by some capital D, the diameter of the data set is capital D, then essentially this one Wasserstein bound can be like transferred to this generalization error bound. So you get like 1 over n here and then times something. And so this result is actually quite strong because if you think about it, this is uniform in time, right? And then we also allow non-convexity. And also we allow like a heavy-tailedness. Now like for the remaining time, I hope I still have enough time. I'll mention briefly about like the idea like behind the proof. So the idea is that actually it's possible because like we discovered like well, I shouldn't say we, I should say like Umut actually discovered this applied probability paper So it was only published last year on stochastic process and the application. So our proof technique is inspired by their paper. I know some of them Li Xu and from University of Macau and Chen Peng, a former student of Li Hu. So what these guys look at, it's a different problem. So they are looking at the Euler discretization error. They look at the Euler discretization error. And but they want to obtain a uniform in time Euler discretization error for heavy-tailed SDE. So actually I'll mention that later, why it's related. But for the moment, let's not forget about our motivation. Our motivation is that we want to understand how the heavy tail can help a generalization error bound. So now we already have a generalization error bound. So we want to understand better the dependence of this generalization error bound on the tail index alpha, So how the right-hand side here depends on alpha. It turns out that a lot of parameters don't depend on alpha. For example, if the parameter comes from the dissipivity condition, right? Or it comes from the pseudo-Lipschitz condition, then it has nothing to do with the heavy tailedness, right? So it doesn't depend on alpha. It turns out that the only term that has a singular dependence on alpha, which is the C0 term. Because the C0 term, you can see that you can write it according to equation 22. So we spelled out the C0 term explicitly in our proof. And so we find out that it has a singular dependence on alpha. So because when alpha approaches to 1 or 2, right? So the denominator here can blow up and so that means this dependence on alpha is not negligible. That's kind of fundamental dependence. And then we made a plot of how it depends on alpha. And so the C0 term essentially has this U-shaped dependence on alpha. U-shaped dependence on alpha. And so the U-shape becomes even more obvious when you increase the dimension. But of course, in practice, the dimension is high. So we will have a very clear U-shape, U-shape pattern. Now, this U-shape pattern actually corresponds very well with the inverse U-shape, a numerical experiment. Because in the numerical experiment, it's about the y-axis is about the test accuracy. So the higher, the better the generalization error bound. So here we look at the generalization error bound. So the lower, the better. So that's why the U-shape here corresponds to the inverse U-shape from the experiment. So that means our generalization error bound for heavy-tailed SGD works. It basically is in line with the theory. And then of course this is just a numerical plot of C0 U-shape. So in the paper I managed to add a theoretical result. So this theoretical result essentially just proved that indeed it's U-shape. So you don't need to look at proposition 1. Basically it's just it's a rigorous proof of in fact you will get this U-shape. So essentially we managed to obtain generalization error bound for heavy-tailed SGD, and we find out rigorously that in terms of tail index, it has a U-shape behavior. And that's corresponding to the numerical experiment of the inverse U-shape. And so so this is a much better this is a rigorous rigorous treatment for the algorithmic stability in the presence of heavy tail, instead of just relying on a wide minima phenomena or some kind of explanation. So now for the remaining a few minutes, I'll talk a little bit about the proof sketch. So essentially, mathematically speaking, you are interested in to obtain a one Wasserstein distance between the law of xt and the law of xt hat. And so here, Zn and Zn hat are close to each other. So as I mentioned, there are several technical challenges. First is that the loss function is non-convex, so the f hat is non-convex. And then then Levy process is heavy-tailed, and the second moments blow up. So you cannot just choose a quadratic function as a Lyapunov function. And finally, like we are interested in uniform in time estimate. So we want to make sure that we can allow time t goes to infinity. So that's like a few technical challenges. And as I said, like we basically the proof idea is mainly borrowed from like a different paper. So it's a 2023 paper about Euler discretization. So what we do is the following. So we first start analyzing the semi-group, like Markov semi-group, and try to write everything in terms of like a telescope sum, and using Duhamel principle. So the idea is that let's say you have xt and xt hat, and they're associated with some Markov like a semigroup. So if you are not familiar with Markov semigroup, so essentially the definition of Markov semigroup is that like for any test function, let's say for any bounded function h, PTH is defined of expected value of xt starting at x. And similarly, you can also define PT hat, the Markov like a semigroup associated with xt hat. And so what we are interested to look at is that we want to look at the test function h to be like one Lipschitz. The reason we want to look at one Lipschitz is because like we want to obtain like one Wasserstein bound. So if you are familiar with Wasserstein distance, you know that for one Wasserstein distance, it has some like a dual representation and some like a one Lipschitz like a test function types like a formulation will show up. And then so essentially the point is that I look at the Pn eta hx minus p hat and eta h of x, right? So in some sense, I want to show that they are close to each other. And then you first write in terms of telescope sum using like the property of like the, and then you use the property of the like Markovian semigroup, and essentially you reach this step. Essentially you reach the third line here. So you want to analyze the third line here. Now, if you want to analyze the third line, you will notice something. Okay, first, this term shows up like a p eta minus p eta hat. So that's just one step like a Markov semigroup, like for the two process. Now, for this this guy here, you need to show it's small. You need to show it's small. Why it's small? It has to be small because like the data set Zn and the Zn hat are close to each other. So you can use that and then some pseudo Lipschitz condition type argument to show that p eta and p hat eta is small. And then you have this term, Pn minus I eta h. So this guy, you want to make sure that it's not, it cannot grow as n grows. Because if it grows as n grows, you will not get a uniform in time estimate. So you want to control these. To control these, you need some like essentially some geometric ergodicity type stuff. You need to have some Lyapunov function to make sure that like this guy does not like this guy does not grow. And then finally, you also need to make sure that under p hat it doesn't grow. Under p hat it doesn't grow. So basically, you can see from here that like what are the ingredients that you need. So once you have this estimate, then you can easily estimate the one Wasserstein bound, because the one Wasserstein bound is essentially like you take the supremum over all the one Lipschitz test function between these two like a semi-group, between these two semi-group. And then the problem essentially just boils down to estimating this stuff, try to make sure that like they are small. Try to make sure they are small. And so the first like lemma, as I mentioned before in our paper, is that basically we are able to show that like for the, if you just look at like one step Markov chain, and they are close to each other. They are close to each other. And then remember that we need to obtain some geometric ergodicity, right? Geometric ergodicity to make sure that it doesn't grow like as time grows. For that, actually, we can just borrow directly some geometric ergodicity like a result from Chen et al.'s paper. So that means like you have some Wasserstein contraction. So you have some Wasserstein contraction for both the xt process and the xt hat process. And actually, this is not enough. This is not enough. So somehow in the proof, you will find out that you also need to estimate the gradient of the like a semigroup, the gradient of the semigroup. But for that, we can use directly from Chen et al.'s paper. So they need that for discretization. So we also need that for our purpose. for our purpose. And then the final piece, the final technical lemma that we need is essentially like some uniform, like in time bound on the expected value here, So you need like a uniform, like in time bound here. And then you need to make sure that basically like the C0 here can have an explicit formula. So in order to obtain like these type of results, you need to construct like a smart like Lyapunov function. So it turns out that one Lyapunov function one can use is the square root of 1 plus like x squared. Because if you are familiar with like those Brownian motion driven like Langevin literature, people often use like a quadratic case when people deal with like overdamped Langevin for Lyapunov function. But because we have a heavy tail, so quadratic cannot work. And if you just naively choose like a x like a norm, and then basically it may not be differentiable. It's not Lipschitz. There are a lot of like bad things happening. So the clever choice is actually 1 plus x squared, then take a square root, and then everything will work. And then you can, we in our paper, we are able to verify, okay, you satisfy some drip condition. So when you apply this Lyapunov function, and you can spell out like a lambda 1, q1, etc. with complete like explicit formulas. And so L alpha and L hat alpha are infinitesimal generators of xt and xt hat. And this helps like establish like a uniform in time up bounds for the expected value for the Lyapunov function. But remember that this v of x is like upper bounding like the norm of x. So that means that you also obtain the uniform in time like up bound for this like norm here. So this is essentially like the idea of the proof. And so how we are able to show like uniform in time like Wasserstein stability for heavy-tailed SGD. So I think that's the end of my talk. Thank you very much.
Thanks a lot for the talk. We might have time for a quick question. Or if not, we could just thank Lingjiong again.
Sure. Thank you very much.